As I said, I think we're all very lucky to have Professor Moomaw here. I've been following Professor Moomaw, some might say stalking Professor Moomaw for decades. Many of you may or may not know that Professor Moomaw was a lead author on the Intergovernmental Panel for Climate Change, the IPCC report of 2007, which won a Nobel Prize. So we have a Nobel Prize. A lot of you may not know that Professor Moomaw was one of the first people in Massachusetts to design and build and live in his own net zero energy house. And it's really amazing, and he can give a whole talk on that. There's very little about climate or energy or sustainability that he doesn't know something very interesting about. I've had an opportunity to hear him talk about divestment, about soils, about anything you want. There'll be plenty of questions. But I'm very fascinated to hear what he has to say tonight about sustainability in our soils.
Thank you.
Thank you.
Thank you, Mark. Actually, there was I got my PhD at MIT, and after the...
Use the microphone, please.
I think, is this on?
Yes.
Oh, okay. All right, I'll get closer to it. When the Nobel Prize was awarded, since all MIT graduates who were part of that whole process were invited to MIT for this big celebration. And we were introduced by saying, well, remember, it was only the Nobel Peace Prize. It was only for peace. Well, so be it. So be it. We used to always joke that if any of us could actually prove that global warming and climate change was not happening, we would win a Nobel Prize. And then darn, we got it for peace. When it proved that it did. I have spent half my career as a chemist, and the second half applying the science I knew to issues like stratospheric ozone depletion, climate change. And in the climate change issue, what I got really fascinated about was what could we do to address it? How could we, as the scientists say, mitigate it? How could we prevent it from getting worse? And since something is happening, we are in a changing climate right now, what could we do to adapt and be more resilient to it? So putting those together, I worked for a long time on renewable energy, which my wife and I got very excited when we had an opportunity to build a home, to build what turned out to be, we didn't start out, we said we wanted to be as efficient as possible, we wanted to use as much renewable energy as possible. And with the engineer Mark Rosenbaum and architect Bruce Coldham, we had a meeting, next to final meeting, and Mark said, I think we could be net zero. And my first question was, can I afford that? And he said, it's not going to cost much more. We're almost there. And so we did build a house, moved in 11 years ago, and it's been functioning. We had startup problems, and let's be honest about it. The ground source heat pump didn't work the way they promised, and we finally got it replaced, and now we have one that works really wonderfully. So it's great to be sending those electrons out to the grid and only drawing them in at night, and over the year putting out more than we put in. But I began to realize that even if we all went to zero emissions, the amount of carbon dioxide that's already in the atmosphere is more than we should have, right? We have, I mean, just look around. I mean, look what's happening. It's not a pretty picture anywhere in the world in terms of what the changed climate is doing to people and doing to our natural systems. And pretty soon a lot of us realized, well, we're going to have to not only stop putting it in, we're going to have to start taking some out actively. And there are all kinds of schemes, and places like MIT, they've got a technology for this and a technology for that. These are all very complicated, they're very expensive, but there's a technology that's been around for about 300 million years. It's called trees. And it's been tried and tested, and it's a great remover of carbon dioxide and a great sequester of it. In the wood is 40 to 50% carbon, and also our soils. Soils have, depending on the type of soil, different things. I just came from 4 days of a wetland soils conference out in Denver, and you know, it's quite remarkable. There is more carbon stored in soils, 3 times as much as is in the atmosphere right now. And a lot of that is in wetland soils and frozen wetland soils known as permafrost. And therefore, it is vulnerable. As the earth warms up, it gets released. So we really have to make sure we don't warm up too much, and we have to figure out how we can get stuff more of the carbon in the atmosphere back where it belongs. By the way, 1/3 of all the carbon dioxide that's in the atmosphere has come since 1750, since the start of the Industrial Revolution, from soils and deforestation and the draining of wetlands. That's pretty astounding, 1/3 of it. We think of it as being a fossil fuel problem, and it certainly is, but 1/3 of the problem is what we've done in the past. So one day, I sort of woke up and I said, what if we could put some of that carbon back where it belongs? And that's what got me on this track, the role of forests and soils. This is a picture of a typical New England forest. Those trees are 75 to 100 years old. That means they're not original. They didn't come with the original real estate. It's been changed by others. Here's another picture showing that we're kind of a rocky soil place as well. And you'll see I'll show you some interesting things that have happened to our forest here in Massachusetts over the years. Now, there's too much on this next slide, but have you thanked a forest today? Right? I mean, you think about it. 1/4 of the oxygen we breathe comes from forests. That's pretty interesting, isn't it? You know, just imagine if you were only getting 3/4 of the oxygen you now have. We'd all have a little trouble breathing. They provide remarkable materials and other resources. I mean, wood, it's an amazing material. It's beautiful. It's nature's composite material. It took us, I don't know, I guess since, we've been around for a couple 100,000 years. It took us 200,000 years to figure out that it was that we could also make composite materials, and nature's been doing it all along. They are the most biodiverse ecosystems on the planet. This is where all the species of plants and animals, not all of them, but many of them reside. There are others, of course, that reside in wetlands and grasslands and of course in the oceans, but on land, it's where most of them are. And intact forests control flooding. I drive back and forth between Williamstown and here at least once or twice a week. And during Hurricane Irene in 2012, Route 2 was cut in about 5 places by just landslides and flooding and everything else. It took 3 to 6 months before it was open again, depending on which section you were on. But it was interesting to note that in the places where our oldest growth, oldest forests in western Massachusetts along the Mohawk Trail were intact, there was no erosion, there was no cutting of the road. It was where the younger forests were that it was being, it just couldn't hold the soil. They prevent erosion loss, clean the air of pollutants, they cool the surrounding areas. And this is where urban trees make a difference, or city trees or town trees make a difference. It can be 5 or 6 degrees cooler because if you have a lot of trees, because as water evaporates from trees, it takes heat away. And then of course the shade prevents those, I don't know why we chose black for streets, but anyway, those black streets from heating up so much. And then for the climate issue, of course, the most important thing they do is capture carbon dioxide from the atmosphere. Everybody will all remember our, whatever, 4th or 5th grade science class about photosynthesis, and isn't that amazing? And then you forget about it until you're an adult and you realize you're going to address climate change. And then we can see that trees and plants are doing the job. Forests provide recreation, scientific knowledge, aesthetic, cultural, and spiritual experiences for people. In the simplistic, trees take in carbon dioxide, they release oxygen. It's a wonderful thing. Sunlight drives it. How simple is that? How cool is that? What a great technology.
Thank God.
Amen. Of course, we use it for building materials and for beautiful pieces of furniture like this. Whenever I see a piece of furniture like this, I think of the, I cannot remember his name now, a Danish designer in mid-century, mid-20th century, who said that he hoped his designs were good enough to justify killing a tree. How's that for a statement? Not your common commercial sense of trees. And here's just a little biodiversity there, right? And here's water and the whole business of controlling water and managing water. On the other hand, when we have flooding, it's in part because we have just basically cut away too many trees, paved over too many areas. You know, I like to think of this as there's a continuum. You think of a forest at one end and a parking lot at the other in terms of its biological function, right? That's kind of the spectrum we have. And unfortunately, we as civilized, modern, technological humans are closer to the parking lot end of this world than this green world. And this is the result that we have. This shows a clear cut in North Carolina, actually to produce carbon neutral wood pellets for the United Kingdom. You can see what happens to water, among other things, when you don't have anything to hold the soil. And the Dogwood Alliance is a local NGO group down in North Carolina that has been documenting this for a number of years. And I'm actually over in London. So I've been invited to come over and talk to some of the officials there about wood pellets and their climate implications. And the head of that organization, Anna Smith, was there. And I was really impressed that this is an NGO that really wants to get the science right. So I've been working with them, and Dan and I published a paper last year on American forests. We hear about tropical forests all the time, but what's happening in America? So we published that in March a year ago. Recreation and health, all kinds of things about health. They've monitored people. Go for a walk on a treadmill, go for a walk on the street, go for a walk in the woods, measure your vitals. Dramatic difference. The forest is extraordinary, and it's cross-cultural. These experiments have been done in Japan, they've been done in the United States, they've been done all over the place. There's something about forest that is very soothing and lowers blood pressure. It's really quite remarkable. So how are our forests doing? Well, this shows the areas of degradation. The light color is what it looked like 8,000 years ago. The dark green shows the last remaining intact forests in the world. We have really done a job on the forests, we, the people of the world. You can see there's still a patch, but it looks a little moth-eaten down in the Amazon. But look at North America. How much, less than 1% of original intact forest exists in the lower 48 states. Less than 1%. And of course, what is that? Well, we protected a patch of redwoods on the west coast in a national park, Sequoia National Park, big trees there, we saved those. But, you know, here in the Northeast, they're just some tiny little patches you can barely see on this map. If you look at air forest disturbance, we all know the Amazon, it's awful. Oh my God, how can they do that down there? You see where the arrow's pointing? That is the most disturbed forest in the world. It's in the United States. And we act like, oh, those primitive people in developing countries, how can they dare destroy their forests like that? We're doing it for money. That's all we're doing it for. The disturbance in the southeast United States is 4 times the disturbance of the Amazon forest. 4 times. And hardly gets any attention at all. If you look at the evolution, 1620, we don't know what that date is. You know, big, just a year and a half, we're gonna have a big celebration, right? 1620, Plymouth, Pilgrims, all that good stuff. We'll have all the great stories told again. 1620, that's what the forest looked like in the 48 states. By 1850, the whole eastern part was gone, totally cleared. And by 1926, even most of the western part was gone. And by 1990, you have just little tiny patches left of original forests. And this has all been done because of the commercial value that could be obtained, and without any thought of any of the other values that were on that first slide. Or not first slide, but that earlier slide. So, 28 species of birds in dependent forests became extinct. Things like the passenger pigeon, Carolina parakeet. We used to have a native parrot in this country. It was gone by the time. I think Audubon was able to paint a few, and then they were gone. Passenger pigeon used to darken the skies with these massive flights going over. Gone. By 1914, Martha, the last one in the Cincinnati Zoo, died. The Ivoryville Woodpecker, we had a little excitement a few years back when somebody thought there might be an Ivoryville Woodpecker somewhere in Louisiana in the swamps. And it was this touch and go. If we find it, should we tell anybody? Should we not? You know, if we do, I mean, if the somebody will want to shoot it to have the last one or something. So anyway, nobody ever found it. It was never verified. But we've been fortunate in the Northeast that around the 1830s, the Ohio Territory opened up. And you could be a farmer in Ohio where all you had to do was cut down the trees. You didn't have to dig rocks every year. Right? Our New England soils are rocky, we know that. Actually, I built my house on top of what is clearly a glacial moraine. We had so many rocks dug out that I built stone walls everywhere and had 2 truckloads hauled away. I couldn't get rid of them enough. I mean, they were just amazing. The fact that this was one time a poor man's farm is amazing to me. I don't know how they grew anything on this land. I've been trying for the 10 years we've been living there to get things to grow, and it's not easy. Connecticut and Massachusetts, Connecticut's about half forest, in Massachusetts about 60%, but we've had a decline in the US about 9% from 1990 to 2012. That was the last date I could find data. It's terrible. We don't keep track. We don't even count our forests the way we should. And this is just showing the distribution of percent of total forest land and the age. Along the bottom is the age. And you'll see in what they call the north, that would include us, that the average age is what, around 65 years. 65 years. In the west, it's kind of a strange distribution. Really young trees, that's all those national forests out there that they manage for timber production. And then there's this bump in the middle, and then you've got the sequoias and those old trees which have been protected. So 65 years, I mean, I look in this room and there are people here who are in that age range. So this is you. Are you ready to be harvested? Everybody's concerned that we see, there's been all the fires in the west, the upper right one there. There's been wind damage in the south. Land's converted, a lot of it in the Pacific Northwest. But some of it here, a lot in the east too. It's not as densely done as in the Northwest. Insect damage, bottom left. Drought, several places. Wind, several places. But upper left, that's the carbon loss from just harvesting trees. Just forestry, just practicing forestry. That is by far the greatest. 85% of the carbon loss is from our timber industry. And 15% is from bugs and wind and fire and everything else, tornadoes. By the way, we had a tornado hit us about 3 weeks ago out in Williamstown. and a enormous, about 120-foot tall triple trunk pine tree came down, took down 2 or 3 huge beech trees. It's the most incredible thing I've ever seen. Fortunately, it was off in our woods and not by our house, but it was pretty impressive to see one of these giants fall. I didn't see it fall actually, but to see it felled by nature. So that's pretty striking that our timber industry is is a significant contributor to carbon dioxide. In fact, if you look at the total emissions from the forest industry, it's about the same as the fossil fuel emissions from our commercial and residential buildings. All the oil and gas we burn for heating our homes. That's pretty astounding, right? And that's from an industry that claims it is working to address climate change. Now, if you look at forest cover in the Northeast, this is area where there are forests, okay? Look at Maine. Oh my goodness, look at Maine. But look at western New England. In fact, look at eastern New England. Then here's the Connecticut Valley, which is farmland. And then here's western Massachusetts, Connecticut, up into Vermont, and over here into New Hampshire. And that doesn't tell the story, though. The story is how much carbon is there in those forests? How much is there per acre? What I have is actually something put out by the Forest Service, the U.S. Forest Service, and they do it in per hectare. A hectare is roughly 2.5 acres. But the relative numbers are what are important. This is what it looks like. Down at the bottom, it's 40 metric tons per hectare, and at the top, it's 130. Look at Maine. It's all pink. Look at western Massachusetts all the way to eastern Massachusetts to Lexington. It's dark green. It's 110 to 130. 3 times the carbon density in Massachusetts as there is in Maine. How is that possible? How is that possible? Maine has had a paper industry for 150 years or more. They never let the trees get very big. Because you can take a tree this big around and ship it up and turn it into fiber and make paper out of it. What happened in Massachusetts is actually a fortunate accident of history. And I'll show you some pictures in a moment to prove my point. If you go to western Massachusetts, go to places like the Mohawk Trail State Forests, there are still some remnant uncut forest, old trees, 400-year-old trees here in Massachusetts. And then there are other places that were cut between 1750 when western Massachusetts was settled up to about 1850, and then everybody dropped their axes and headed for Ohio. And all of that land reverted. So there are now forests out there that are 150 to 200 years old. I'll show you some photos in a moment that are astounding. That's why this density is so high. But we have a problem. I just heard an official of the Commonwealth of Massachusetts say the other day, well, we have too much older growth in our forests in Massachusetts, and we need to have more early successional stages, because that's how we will protect the New England bunny rabbit and the woodcock, and there's a third species I forget now, and we only have 4% of our state forests in early succession, and it should be 10 or 15%. And besides, we will replace all those old trees that are just waiting to die with young, vigorous trees that will grow rapidly. You've heard that story before, right? Haven't you? You know, fast-growing young trees? All right, we'll take a look at that in just a moment. But this is astounding. When I came across this, I thought this was quite incredible. And now I'm actually chairing the board of the Woods Hole Research Center, which is a scientific research organization founded in the 1980s by George Woodwell, a really, really fantastic scientist. And they have been working on climate change and forests and wetlands and soils since the 1980s. And I will quote some of their findings. They are actually have an improved version of this, which will be coming out in the next year for the Northeast. And we'll be able to see down to a level of 100 feet resolution.
Wow.
So if you have a piece of property that's bigger than 100 feet, it'll show up as more than 1 pixel. All right. Well, just a little review. I know everybody knows about climate change. Just a little quickie here, because I'm going to show you something quantitatively that you understand qualitatively, but it's important to know how it works quantitatively. So these gases that go into the atmosphere, they're only trace amounts. I mean, we're only at 0.04% with carbon dioxide, and before that it was less than 0.03%, but that increase, we're now up about 40-some% above pre-industrial levels, and look at the difference it's made. Plus we've thrown a lot of other things in there, like our fluorofluorocarbons and things like that that we have as well. And the Earth's temperature is regulated by these very small quantities of heat-trapping gases and water vapor, by the way. And although we're not putting a whole lot of water vapor in, as the Earth warms, the ocean warms, there's more water vapor. So we now have 5 or 6 or 7% more water vapor than we had before, and that. So for every degree of temperature you raise by the direct heat-trapping greenhouse gases, you get another degree just from the water vapor that's released. And this sounds trivial, but you'd be amazed how many people don't get this, even very smart people. If I were to tell you that if we, what would happen to the concentration of carbon dioxide in the atmosphere if we reduced our emissions? Some people would say, that's great, the concentrations would go down. But they forgot about one other thing. And I'll show you what happens in fact. So those gases trap the heat and radiate it over on the right there, those sort of orangey arrows. They absorb the heat as it comes off the Earth. It's heated by the sun, and half of it gets radiated out to space, but half gets radiated back to Earth. And here, astounding fact, on a given day, we get twice as much energy radiated back from the atmosphere as we get directly from the sun. There's so much heat that's absorbed up in the atmosphere. And so carbon's the currency here, right? This is what we have to keep our eye on. Where is the carbon coming from and where is it going? And you can see here, we have about 860, that's billion tons. We're putting about 9 in directly every year from burning fossil fuels and industry. And then land use change is another 0.9, or about 1. That's from burning forest, clearing forest for agriculture or for urban development. And so 9 and 1, 9.9, that's roughly 10. We're putting in about 10. The land sink, as it's called, is taking out about 3, and the ocean's taking about 2.6. So we wondered when we began measuring all this, why, if we were putting in, let's say now 10, why only 4.5 or so was appearing in the atmosphere as an increase? And in fact, 10 is going into the atmosphere, but nature is taking out half of it, a little over half of it. Or to put it another way, we are putting it in twice as fast as nature can take it out. And the sinks for this are interesting to look at. Where is it? Well, forests are storing about 600 billion tons, but soils are storing 2,200 billion tons. So almost 4 times as much as in soils as is in forests. And yet the picture always shows forests. And they're very important because they're the sucker-uppers, right? I mean, they're the ones that bring the carbon dioxide in. The plants are what bring it in. And some of it's stored in plants, but a lot of it gets stored in soils. Because when trees die, they decay, and they become soil. A little bit of it goes back in the atmosphere, but most of it becomes soil. When leaves fall, Isn't it interesting that they don't, we'd be up, can you imagine living in New England with leaf fall for 400 years, where we would be if nature didn't do something about it? I mean, we would be right under leaves here. We would be drowning in leaves. And so they decay and they become the rich black humus that many of you I know probably compost your leaves or compost your garbage, whatever it is, your waste, your leftover food, whatever it might be. But we have 10,000 billion tons, more or less, in oil and coal and gas that we can put in the atmosphere. So we could really do ourselves over if we use it all. And the atmosphere, just showing how the atmosphere works, it's like glass in a window. If the glass were the carbon dioxide, the visible light comes in, the radiant heat tries to come out, the glass blocks it. I was just out at this conference in Denver, in the hotel, they had a gas fireplace going day and night, 24/7. But it was inside two glass panels. There was no heat coming out of it at all. Interesting. It was great for my talk. I could just show everybody what's happening. Now, that idea was understood in 1827. So this is not new science we're working with here. 1827. It was called the greenhouse effect because it was like a glass house that you grow plants and things in. And on a sunny day, it's warmer in there than it is outside. So you can start your plants earlier. Your gardener. I see gardeners in this room. I can tell there's a gardener. But if this had been thought of in 1927, it would have been called the hot car effect. This is something put out by the Humane Society. Don't put your dog in a car and close up the windows on a summer day. It's like putting him in an oven. It's exactly like putting him in an oven. These numbers are just astounding. So if it's 75 outside, in 10 minutes it'll be 100 degrees inside. If it's 100 degrees outside, in 15 minutes it'll be 140 degrees inside. So, the hot car effect, remember it. I thought this was great. Death Valley, caution, extreme heat danger. I guess it is. Look at that. Boy, look at the heat distorting the air. Well, here's the record of carbon dioxide that you probably all know about. It's called the Keeling curve, after David Keeling, who discovered it. He was a PhD student at University of California at La Jolla. And think about this. See here, if you only had the first 3 points, which are the little uptick on the left side, perfect. Every month, that's the monthly average, it goes up. The next month, though, the 4th month, it went down. And the 5th month, it went down. And the next month, it went down. It went down for 6 months. And then it turned around and started going up again. Poor David, he must have just panicked. These are the things that just make a scientist, particularly a young one, just, what have I done wrong? But it turned out what he was seeing was the breathing of the northern hemisphere, because he was actually in Hawaii, which is the northern hemisphere. And so in the summer, spring and summer, plants draw down the carbon dioxide. In fall and winter, they release carbon dioxide. And so you get this oscillating pattern. And the long-term trend is the fossil fuel-driven economic development of the planet. There it is. And the deforestation. And the destruction of wetlands. And the destruction of grasslands and soils. So that's the history of our planet written in the atmosphere. And the temperatures have just increased pretty dramatically. They bounce around a lot. It doesn't show up very well there. You can see little dots there. That's the average global temperature for each year, meaning you have to send in, I used to frighten my students by saying, okay, on the final exam, the question is going to be, if you need to measure the average global temperature, where do you put the thermometer? And of course, the answer is everywhere you can. And so there are now something like 7,000 sites that send things in. But when I started this work, there was no internet. And it was all done on little pieces of paper and in lab notebooks. And then by, I don't know, teletype or something, it was sent into to some place, and people kept track of it. So it goes up. Now you see the little step there at the end where it levels off on the right-hand side, just before the last 4 or 5 years. All right, that was the end of climate warming, according to the skeptics. You see, it's not happening anymore. And, they were really vicious on this. So we don't need to worry about it. Never mind that, from about 1950 to 1980 was pretty flat also for a 30-year period. And there are other things that are happening. Like there, we were putting a lot of soot in the atmosphere that was blocking sunlight. So it didn't warm up properly, as it should have. And so then soon whatever, nobody's still quite sure why it leveled off that little bit, but it zigs and zags. But now look at it, we're up there. 2016 was the warmest year on record, and 2017 was down just a little bit. So 2014, 15, and 16 in a row were the warmest years. What's the probability that will happen randomly, do you think? It's pretty low. Could happen. 1 chance in 100, 1 chance in 1,000, I don't know what it is, but anyway. So when we came up with the climate treaty in 1992, the goal was the stabilization of greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. All right, people, you got to quit putting it in. Right? We got to do something like, we have to control the concentration. How do we do that? Well, here's the problem. In Paris, in 2015, 80 some countries did their nationally determined contributions. That's diplomatic. Notice it's not commitments, it's contributions. This is diplomatic language to get everybody aboard. And so if we'd done nothing, temperatures would have risen to 4.5 degrees Celsius or 8 degrees Fahrenheit by 2100. With the commitments made in Paris, it'll only be 6 degrees Fahrenheit warmer than pre-industrial levels. We said in the Paris Agreement we would stay below 2 degrees or 3.6 degrees Fahrenheit. And we would try to stay at 1.5 or 2.7 degrees Fahrenheit. We have a ways to go here. There is a gap. Good news is, starting already, by 2020, every country has to come back in and say how they're gonna ratchet up. What are they gonna do next? I don't think the United States is going to be there for that. We have pulled out, or we have said we're going to pull out. So this is the dilemma. And so how do we have to think about this? Well, John Sturman at MIT and his students have done some wonderful thinking about this, and they developed this little conceptual model to show you how this all works. So think of carbon dioxide in the atmosphere as water in a bathtub. There's a faucet at one end and a drain at the other end. How simple is that? The drain is open, the faucet is on. And depending on how fast it's coming in and how fast it's draining, the water either rises up, or it goes down, or it stays the same. If the rate in is equal to the rate out, it will stay the same. As I said, we've got the faucet running twice as fast as the drain, and we need to find the equivalent of Drano to change the situation. That's where forests and soils come in. So here is an example. On the left, the blue line, beginning in 2000, we were putting in about 7 billion tons. The world was putting about 7 billion tons. If we continue on that trajectory, we'll be up around 21 billion tons by 2100. The blue line shows how the concentrations would change. And this assumes that we don't destroy any more forests and things, by the way. Okay, so there's an assumption built in there. And so we were below 400, we were around 380 or something in 2000, and we would be up around 750 parts per million, right? So we would double by 2100. And so somebody said, well, what would happen if we just kept the concentrations constant immediately? By 2020, we just made it constant. Well, look on the right-hand side. Okay, it doesn't go up to 750, but it still goes up to about 575, which is still way, way more than we should have. Okay, so that's the problem. And there's if on the other hand, if by 2050 we reduce our emissions dramatically by 80%, we would come in at about 450 parts per million, which is 40 more than we are right now. And we're gaining 2 or 3 or 4 a year. So that gives us something like 10 or 20 years to do this, to get going on this trajectory. and really get down 80% by 2050. That would do it. That would stabilize it. That's still more than we need and more than we should have. And so we're going to have to do something about that. Well, it turns out, let's see, there you see it. Emissions become equal to removals, and that's how it stabilizes. The drain is now able to cope with what we're putting in. That's all done on the reduction side. But it's still too much. So if you look at what was happening, there's the red is what was going into the oceans, the blue is what was going into biomass or into forests and soils and things. And if we were to add some forests or some wetlands or some soils that could sequester about that amount, what would it do? And it would start bringing it back down. So we shouldn't do that sequentially as I described it, we should be doing both at the same time. So that's about 1.6 billion tons per year. We can get that easily by just letting trees grow. If we just let some of our secondary forests grow, we could easily get 1.6 billion tons a year. If we restore degraded grasslands, we could get another billion tons. If we were to restore some of our destroyed wetlands, not let people put the clam shack right there by draining the wetland first, we could get probably another billion tons. Interesting, right? That would be actually enough to get us into the balance range. And then everything we didn't put in would bring everything further into negative territory, and we would keep going down like this. So that's what we have to do. Now, in the UK, they're very proud of themselves that their emissions of carbon dioxide fall to levels not seen since 1894. This was a headline in the London papers when I was over there. However, this is the biggest coal-burning power plant in all of Europe, and they've already converted half of it to burning wood instead of coal. But they counted as zero. Isn't that interesting? Counted as zero. Now, I don't know how many people here have had a chemistry course, but if you burn anything that has carbon in it, you get carbon dioxide. I'm a chemist, I can't give that up. I just cannot give that up. And so there they are. They're burning now up to 6 million tons a year, and all of it is coming from the United States. Because if they got it from Sherwood Forest and the rest of the forests in Britain, they'd use it all up in about a year. There aren't any forests. They're so proud. They planted a national forest in the 1990s. And they're planning another one that will go from coast to coast. And I'm doing calculations now to see just how much carbon that will take up. I think it'll take up about maybe an hour's worth of what they're burning from the United States. I mean, it's a few hours. It's really atrocious. And here's what they're burning. The red is the wood pellets. And so there's this huge wood pellet industry growing in the southeast United States, and it's coming this way. Maine is, because there's no more paper industry, they are going to chop down their forests and turn them into pellets. Now the Europeans won't accept Maine pellets because they have an insect in them. So the clever folks at the University of Maine have developed a cooker that will sit inside the ship that will burn natural gas all the way over to heat and cook the wood chips to send them over there so they can be burned and be carbon neutral. I mean, I'm not making this stuff up. It's just astounding the lengths to which people are going to say that this is a wonderful thing. Now, I thought it was great. I mean, I went back in the oil crisis of 1973. Like a lot of people living out I was teaching at Williams at that time, Williams College out in Williamstown. I got a wood stove, and we thought we were so superior to all those people, poor people whose oil bills had quadrupled. And yeah, sure, another tree will grow, so therefore, it's carbon neutral. It's great. Didn't do the math properly. You've got to do the math properly. And when you do the math, you realize that in fact, it's really bad. It's really, really bad. Again, here's what it looks like in in North Carolina. This is another area. You can see a close-up there from the ground. You know, the wonderful thing about NGOs is they go out, now they have drones, they have cameras, they have video. I mean, all of us are now, you know, we are all now videographers with our, we just get out this little thing here and we can be a videographer. We can do all these things and they present them. And we in the scientific community finally look up and say, oh, look at this interesting evidence that we didn't think of before. It's all out there. And this is the one I showed you before, the devastation and the statement made by the company Enviva. Enviva suppliers take extra care by using specialized harvesting equipment and techniques that minimize environmental impacts and protect soil and water quality. That's on their website. That's directly from their website. There have been two documentaries now, one done by a group up in Marlborough, Vermont, and then Channel 4 in London came over to do a documentary, and they showed that in London a month ago. And they were out there, they would go to one of these sites that was being cleared, and then their photographer would watch them loading the whole trees on the truck, follow them to the Enviva plant, and show them going into the Enviva plant. Then the drone would fly over and show the piles of logs, and meanwhile Enviva says, oh, we only use forest residues and sawdust to make pellets. All right. I did a blog through the website, The Conversation, on this, and I don't know how many people were in, Professor, you don't understand how pellets are made. They're made from sawdust. Well, that used to be true. It is not true anymore. They're chipping up whole trees. The new statement is, we only take misshapen trash trees. I love it. Every tree on this place was a trash tree. It was misshapen. It wasn't suitable for anything. Not even for that owl I showed you. Right? It couldn't be used by anybody. And GWAC, the company in Britain, says we never caused deforestation, and that's now captured in a video, and it's really quite extraordinary. And here again, thanks to the Dogwood Alliance, you see those diseased trees there. You can look at the butts of the trees there where they've been cut, and you can just see how diseased they are. And you can see that they're small and misshapen and everything else. And there it says Enviva right there. Another student of mine happened to be in Panama City, and she got pictures of them GWAC trucks loading the logs onto barges to go to England. 4,000 miles. They built, not barges, ships. They built 4 ships just to keep shuttling this stuff over. And then there's a special train that takes it from the port to the power plant. I mean, you think of the expense. There's so much invested in this, they can't turn it off. They won't turn it off. Now you might think, well, this is really cheap and therefore they're doing it. No. Without the $1 billion a year for this one power plant, this would not, the subsidies by the British taxpayers, this would not be being done. Okay. We in Massachusetts are about to do the same thing. There is a provision called the Alternative Energy Portfolio, and there are all kinds of subsidies for burning wood. All those poor little communities out in western Massachusetts, all their schools are going to burn wood. All their children are going to get lung cancer, but that's okay. It's burning wood, it's fine. Lung Association says, don't do it. The health effects are too bad. I was just at a meeting Friday and Saturday with a whole bunch of people from all over the country. The new battle cry is forests, climate, and social justice. Because all of the pellet mills are built in poor communities, mostly African American, in the Southeast. And the problems, the health problems and everything are just severe. So there's going to be a new movement, a new wave coming, which has, based in the science of climate change, but also calling for equity and fairness. So here's a pellet plant. Now, some of our legislators introduced a piece of legislation called the Mohawk Trail Partnership, which was premised on building pellet plants in western Massachusetts. You can see what a nice, you see look at those are not little cigars down there, those are whole trees, all there at the bottom, and so on. Yes, there is sawdust. That's after they've chopped these up and made them into sawdust, and then they made into pellets. And there's another picture shown from the air, and you can just see the whole layout. It's enormous. 850,000 green tons a year of trees goes into that process. So that's a serious problem, and it's a serious problem here. Portland, Maine is setting itself up to be an exporter of pellets to Europe. And when they wiped out Maine, heading this way. This is not a good idea, I think. Restoration can take place, but it looks kind of monotonous, right? These are, you can tell what a tree, they're basically tree farms, and you can see the lines of the older trees and the replacement trees. We don't really need to do that. Now what I'm going to show you is some good news. About 4 months ago, I was giving a talk in Northampton and to a land trust that, let's just say they had sort of a mixed record on how they were managing those lands, all right? And so I knew there was a fellow here in Massachusetts named Bob Leverett who he's a retired Air Force engineer. And being an engineer, engineers like to measure things. So he and his son set out to find all the big old trees in the northeastern United States and to measure them. So he now has this very expensive laser rangefinder where he can measure the top of a 170-foot tall tree to within a half an inch. And he has this data going back to the 1990s. So he took me out to show me some of this. So, all right. This is along the Deerfield River in the Mohawk Trail State Forest, your state forest. Those trees, the green deciduous trees, that canopy is 100 feet tall. There are trees in there, things like, he showed me a yellow birch that they had cored that was 380 years old. And sticking out of that are these white pines. They are in the range of 150 to 175 feet tall. This is one of them. That's me in the corner there. And thanks to the panorama function of my iPhone, I was able to sweep up the tree, and you can't even see the top. I mean, it's lost in the clouds up there almost. It's extraordinary. It's 11-something feet around at breast height. And there are 27 of these kind of trees in this one grove. But there are other pretty little things in there too. There's biodiversity on the forest floor. These are some of Bob's photos. So here we are, Mohawk Trail State Forest. This is the Bryant white pine. It is now the tallest tree in New England. That's been measured, at least, that we know of. That's pretty impressive. That's pretty impressive. It's 176 feet tall. And as I was talking to Bob about this, I said, well, do you have any idea how fast this is growing? Because you've been measuring. Oh, yeah, I've been measuring them. Here, let me show you the data. Well, it really blew my socks off, this data. It's really wonderful. So I asked him to put together this slide. So this is the Jake Swamp white pine. It's been named that after Jake Swamp, who was a member of the Mohawk tribe, I guess, because they're all named after famous Native Americans. And so how does this work? You know, we talk about these little trees, they grow fast, and it's great. So you look down here, white pine, from 0 to 25 years, it puts on 124 pounds of carbon. By 50 years, though, it's 1,161 pounds. That's really fast. But between 50 and 100 years, it goes from 1161 to 3709, so it puts on almost 2,000 pounds in the next 50 years. And from 100 to 150 years, it goes from 3,700 to 6,800, which is 3,000 pounds. If I cut that down because it's old and over mature, and plant a little tree, how much carbon am I storing every year compared to that? Foresters do not get this. Many scientists do not get this. So try to figure a way to make this clear. Would you prefer to have a bank account with $1,000 in it, earning 5% a year, or a $100 bank account earning 10% a year? Right? In one case, you get $50 a year, in the other, you get 10. Right? That's the difference. So here we are. We are opting to have early successional forests in Massachusetts to have the $100 bank account with the $10 or the 10% interest. It's just amazing. So that's not the only one. This is a black cherry. Not as tall as the white pine, but it's enormous. It's enormous. So this is what a typical New England forest, a lot of little skinny trees, because the average age is 65 years. And could we let our New England forest grow? And this is from the climate meeting last December. Sustaining and increasing forests is vital to get on track in time to meet the Paris Climate Change Agreement goal, which is to keep the average global temperature well below 2 degrees Celsius and as close to 1.5 degrees as possible. We are already at about 1.1 or 1.2. We've risen above the background. This is written by a Brit, obviously. The maths, plural, of climate science show that meeting this goal is impossible without nurturing forests, which from the atmosphere's point of view are massive sinks of carbon locked up in trees, plants, and the soil, and a source of oxygen through photosynthesis. Okay, this was a statement made by a group of scientists at the last climate meeting. And then Inger Andersen, the Director General of the International Union for the Conservation of Nature, which is an independent organization which is made up of some governments and some, World Wildlife Fund, Nature Conservancy, all kinds of people, and some academics. Our planet's forests are being decimated at an alarming rate. Putting a stop to this destruction is crucial to tackling climate change, reducing poverty, and feeding a growing global population, in line with the Paris Agreement and the Sustainable Development Goals. Sustainable Development Goals were passed unanimously by every country in the world in 2015, and they say things like we have to address climate change, we have to have clean energy, we have to protect the biodiversity on land and in the oceans. And by the way, that carbon dioxide is going into the oceans, as you know, is making them more acidic, which is decreasing biodiversity, and in fact are threatening our whole food supply from the oceans. Nature-based solutions such as protecting and restoring forests can contribute over 1/3 of the total climate change mitigation required by 2030 to keep the temperature rise below 2 degrees Celsius, that's 3.6 Fahrenheit. More decisive collective action is now needed to seize this opportunity. So, we need green trees and healthy soils to keep our blue planet. That's the message, I guess. So, thank you. I'll take questions. Anyone, just raise your hand and I'll, yes, sir.
I want to just make sure I understand something. If a tree grows up and then it dies and falls to the ground and decomposes, doesn't it release methane?
No.
That it doesn't?
No, it will release some carbon dioxide back to the atmosphere. Oh, it will release some carbon dioxide back to the atmosphere when it rots.
Yeah.
But much of it goes into the soil.
To the soil.
So this is, and it's a hard, you say, what percentage? Well, it depends on the species of the tree, it depends on whether it's a wet forest or a dry forest. I mean, but the point is that a lot of it goes into the soil. Right. You notice when all those little branches and things twigs fall off, they're not there the next year. They've gone to their just reward.
What's the difference among species of trees in terms of carbon capture?
Good question. I mean, there are fast-growing trees and slow-growing trees.
You have to repeat the question.
Yes, sorry, the
TV
question. What's the
people
difference
won't hear.
among species of trees in terms of their ability to capture carbon? And there's a huge range. When I first got involved in all this back in 1988, there was actually a former Williams graduate who had been a student of mine, was working for EPA. And he asked me to come over because at that point I was working at the World Resources Institute as the director of the climate program. And he and this higher official with EPA were writing the first report on climate change and what it meant. And they had figured this out, that we needed forests, and their immediate side was, well, eucalyptus are the fastest growing trees, let's plant eucalyptus everywhere. No, I said, no, there are multiple issues we're trying to address here, and so you don't want to just go with the fastest growing one, you want to go with the ones most appropriate for the situation that you're in. I mean, some of the hardwoods grow more slowly, but they're denser. The wood is much denser. Oak is far more dense than pine. And one of the things that we've done is, you know, as Americans, we're always in a hurry, and we want to do things faster. So we figured out how to grow trees faster. So you cut down the natural forest, you plant it all with the fastest growing pine species you can find, and then you sell the lumber. Well, I discovered when I was building my house that I actually used a composite material for the clapboards because I didn't want to paint it all the time. But I used wood trim, and it was pine. Within 5 years, it was splitting, it was rotting, fungus was growing in it, and it was all this pine that had grain, you know, wide grain because it had grown so fast. And my contractor was very apologetic. He said, well, that's what that did. And the architect was apologetic. The engineer, everybody was apologetic, but I had to fork over a couple of $1,000s to replace all the trim with something that wasn't wood, because I couldn't get wood that would be durable enough. So anyway, it's tropical forests grow faster than temperate forests. Temperate forests grow faster than boreal forests. But boreal forests, which as you recall, if you may recall in that picture, some of those are, that's actually probably the largest area that's still intact as a forest. That is northern forests, up in Canada, Alaska, Siberia. But those trees don't, when you cut them down, they can take centuries to regrow. So we've gotten, somebody put that in the bank for us a long time ago as a legacy. I mean, nature did, obviously, they weren't planted. But they were put there a long time ago. And so we have this wonderful storage of carbon thanks to those processes at the end of the last ice age. Yes?
Well, in terms of, you talk about people who are managing forests, I go to Maine, and there are all of these people up there saying, come and we will manage your land.
Yes.
We will cut down this. You know, I'm a graduate of the Yale School of Forestry.
Yes.
To what extent are the colleges, or say something like the Yale School of Forestry, to what extent what do they teach? No, but I'm just trying to say what people are saying, and if you don't know anything, you're saying yes, yes.
Yeah. No, it's a problem. They're basically the whole focus of forestry is to cut trees down. And for example, the National Forest Management Act, Multiple Use Sustained Yield Act. The only use that's specified in the title is cutting down trees, sustained yield. It's not the Biodiversity Enhancement Act. It's not the Carbon Storage Act. It's all about cutting down trees. And so that we have a whole industry and a whole profession that is dedicated to figuring out how to get the most wood out of the forest in the shortest time. By analogy, think about our fisheries. It's a very great analogy between fisheries and forests. Right? We have people trained as fisheries scientists whose job is to get the maximum sustained yield. The terms are identical in both fields, maximum sustained yield. Never mind that I might not know what the conditions are, we're going to get the maximum sustained yield. And the result is we have overfished our oceans and we're overcutting our forests. Meanwhile, you have forest ecologists and marine ecologists who are saying, wait a minute, there's a whole functioning system here. If you just take out all the big cod, you're not going to have little cod someday. And yet, how do we design our nets so the little fish can get away and we'll take the big ones? Well, they've just realized it's those big mama cods that are the fecund ones who are producing the most eggs. A 100-pound female cod produces something like 15 times as many eggs as 10-pound mama cods. And there was an estimate there are probably fewer than 1,000 of those left in the whole North Atlantic. And we wonder why the cod don't come back. We've set up our whole fishing system. Well, we understand we have to let the little fish grow up to be big fish. We've got to let the little trees grow up to be big trees.
So should you just let forests grow, period?
Well, we should let some of them grow.
Okay.
And what we should do is we should protect the big ones that are already there, and we should really look at what are going to be the next big ones, and where will that happen? Well, we have some of those right here in Massachusetts, the third most densely populated state in the nation, and we have the biggest tree in New England. Take that, Maine.
So I love hearing about what's going on above ground with the trees.
Yes.
And I've heard you speak eloquently about the soils.
Yes.
And I wonder if we have a local farmer here, and we had somebody here who's doing compost. We're picking off curbside composting to put things back into the soil. I wonder if you have a little
Sure.
time to talk about
Okay.
the soils.
Yeah, good point.
Would you repeat the question?
The question was about what about soils? I mentioned
Below
soils
ground.
several times, but I didn't really say much about them, except the fact that there is almost 4 times as much carbon stored in soils as there are in trees. And that's all kinds of soils, including agricultural soils. We have about, as I said, about 1/3 of all the carbon dioxide that humans have put in the atmosphere is from degradation of soils and forests. We cut down forests and degraded soils. Out in the Midwest, if you go to Iowa, there's the strangest phenomenon. You go to these little towns there, and there'll be a little white church standing on a platform of land that is 8 or 10 feet above the surrounding land. That's where it was. All the land was at that height when the church was built in the 1910s or 20s. All the other soil is gone. It's either been washed away and erosion, or it has been oxidized directly by air. The carbon material has been oxidized. And you know, those soils are incredibly deep. We haven't hit bottom yet, but it's there. So what can be done? And the answer is a lot can be done. We're learning more and more how to add carbon back into soils through the way in which we practice agriculture. And there are some very, Vermont, I think, now has a program to reward farmers for adding carbon to their soils. Well, they're already getting an increase in productivity when they add the carbon. They get, they're more immune to droughts, right? It holds more soil, the soil holds more water. Productivity goes up by quite a few percent, depending on how much carbon you add back to the soil. Massachusetts has a piece of legislation like that in the works. Whether or not they'll get it out by the end of July, I don't know, but it's in there. Grazing, you know, we've degraded probably 3/4 of all the grasslands of the planet. And people have discovered that if you just let cows and sheep and goats just range out and eat what they want, they're lazy. They'll stay in one place until they've eaten everything, and then they move on, and then there's nothing to regenerate. And so a process, there's several people who've been involved in this. Alan Savory from Zimbabwe, actually. He worked as a game warden in South Africa, and they were shooting elephants that were trampling the grass. And they fenced it off, and he noticed that the grass never came back. And suddenly occurred to him that, in fact, there is no grassland in the world where there are not grazing animals. So what is it that native natural animals knew that we don't? They know you take one bite and move on, and then you leave a little deposit, you know, afterwards. And that is a process that there's several different intensive short-term grazing systems out there that are proving quite successful. I mean, out in Denver, when I was in Denver, we had a field trip and we saw a piece of an area that had been converted to that kind of grazing, and it had been transformed. They canceled the lease with the rancher who was using it before because he was just overgrazing it, and this new sort of episodic grazing, it's just restored it. It's amazing. And the soil carbon increases dramatically, as studies are beginning to show. In fact, there's an organization called Soil for Climate, and Seth is kind of sitting right over there, and that is trying to make this information available. And if we can restore our soils, we'll be able to feed all these extra guests who are coming to dinner between now and 2050 without having to cut down more forests, which, right? I mean, so there are all kinds of positive connections that can be made here if we put it all together. Yes?
Is there any hope for adding forests and soils to the carbon capture legislation that we see aimed at power plants, for example?
Not right now. There should be. One of the things that worries me is I think we should have a price on carbon, but if we put it on oil, coal, and gas and not on burning wood, we will shift. It'll be an incentive to shift to wood. That would be terrible. So we need to, you know, you got to think these things through before you. It was a good idea, but not good enough. And the carbon capture and storage from power plants is we've spent I don't know several $1 billion in the United States, and we have one small thing to show for it, where you burn the coal, you capture the carbon dioxide, and then you pump it in the ground somewhere. And usually it's used to pump in the ground to push out more oil. Well, wait a minute. How can that be called, you know, carbon capture and storage? It's not.
Can you write a piece for the Woods Hole Research Center that we can use to take to our legislators to modify their carbon pricing legislation so that they have the science behind this change they obviously need to make?
We have a meeting, a board meeting is next week. I will raise that.
Thank you.
Good. Yes. Yes. Yes, ma'am.
Is it a worldwide atmosphere, or do we need these forests everywhere, or can there be a concentration of forests in one place that helps the whole planet?
Yes, the good thing is that the atmosphere circulates uniformly around. I mean, it takes, within days, well, you know, when Chernobyl happened, the radiation from that, or Fukushima happened, that radiation was around the world within a week. Now, the atmosphere, north hemisphere to southern hemisphere takes about a year to mix, but it is. Now, the wonderful thing about forests is they are distributed all over the planet, and so they're right there, and we don't have to worry about locating them. They're already located, and no matter where they are, they're absorbing carbon dioxide, which then drains it from the rest of the atmosphere. Right? It takes it and puts it in that particular forest.
Thank you.
Yes.
Has any calculations been done comparing the net impact of burning wood pellets for heat versus oil, natural gas, or electric
Yes, yes. I'm part of a group of scientists who said, you know, we've got to get this out there, because people are doing all these. Well, a tree's growing somewhere. As long as the tree growing somewhere, it's okay. And if we burn it here, it's carbon neutral. And all these hand-waving arguments. So John Sturman at MIT, the one who did the students did the little demonstration thing there, have done it in January. They published an absolutely wonderful paper comparing if you burn wood pellets compared to burning coal, oil, natural gas, solar energy to make that kilowatt hour of electricity. In other words, the goal was to make a kilowatt hour of electricity. You can do it 5 different ways. What's the difference? Found that using wood was about 50% more carbon dioxide than burning coal. About 3 times as much as burning natural gas, and of course infinitely greater than using solar panels. Even if you take into account whatever emissions were done in manufacturing the solar panels, you have to do that also then for the power plant, you're still way ahead. So within a year or so, you've paid back all the energy and carbon you put into those solar panels.
Did your study do particulate matter as well?
That was not part of it, but there are separate studies that look at particulate matter, and the particulate matter is much worse from burning wood than it is from burning coal. And I think nitrogen oxide emissions are worse. Sulfur emissions are better. but that's the only one.
And would the same be true for heating versus generating electricity?
Heating's a little bit better. It's only, wood is only about 7% worse than coal. Yes.
Could you speak to the viability, or maybe not, of the use of biochar as a carbon sink?
Yeah, that's a tough one. I've talked to a number of people about this. Biochar is, it's sort of like making charcoal. I mean, you char it, but you don't burn it. But I have not seen a full analysis of what are the total emissions of making the char. We do know that you can then take the char and put it in the soils, and it will remain for hundreds, if not thousands of years. And so it's a way to store it, you know, instead of having this gas that goes everywhere, you have a solid thing that just puts in the soil, and it actually has some benefits for the soil. But I just don't know what the carbon dioxide emissions are from charring it. Obviously, it'll depend what fuel you use to do it and so on. So. Yes,
Bill, I was wondering if I could just make a quick announcement about Soil for Climate, just to add a little bit to your comments.
Sure.
Could you stand up?
Yes.
Hi, my name's Seth.
You want to come here, Seth?
Okay, that's not it. Thank you. My name's Seth Itzkan. I'm a colleague with WilliamMoomaw. We're very honored to have him on the advisory board of Soil for Climate, and we're research partners with the Global Development and Environment Institute at Tufts University, where WilliamMoomaw is currently the director. And we co-authored a paper which is available in the back. It's called Hope Below Our Feet, Soil as a Climate Solution. There are copies in the back. Of course, you can Google it, it's online. And this was the technical brief, but here's the more common language paper. It's called The Agriculture of Hope, Climate Farmers of North America. And this was in Permaculture magazine, and this is also in the back, and both are available online, of course. Just very quickly about the legislation, it's called the Healthy Soils Act. It is now already favorably reviewed in committee and is part of the environmental bond bill, and it is hopefully will be passed this fall.
State or federal?
This is state. Massachusetts Healthy Soils Act. You can Google that. It was favorably reviewed in committee, and it's now part of the environmental bond bill. So write your legislators and tell them to support it.
And I believe it's the case that the governor is supportive of the bond bill, is that right?
Yes, that's correct.
Yes. Yes.
Thanks, Bill.
Yeah.
I'm wondering if you can talk a little bit about how do we respond to people when we want to balance our carbon budget who say that it's not economical to do it through all this ecosystem stuff. It's too slow and we could never do enough of it. How can we talk about soil recharge rate, restorative ecosystem management
Right.
in numbers?
Right. Well, the numbers are there now. We did not have those 10 years ago, but we do now. And for the soils, you see results within a decade, within less than 10 years. With forests, I mean, you can see, you're adding, 100 pounds or something to the tree of carbon every year. And it turns out to be the lowest cost option compared to all of these wonderful machines that are being devised, which also require more energy. I was amused. There's something called bioenergy carbon capture and storage, which is we would burn the trees I mentioned, and then we'd capture the carbon dioxide and bury it. But in the analysis, they forgot to put in the fact that there's about for every 2 power plants you're taking the carbon out of, you have to build a third one to take out the carbon, and then it is also emitting. And so not only do you have to have a land area the size of the Indian subcontinent to provide whatever percentage of electricity of the world, but you have to have Indian subcontinent and a half to do it for the extra one to remove it. So I have if you go to the conversation, it's just called theconversation.org, and I have a piece on there kind of going through the whole bioenergy thing and the carbon neutrality argument that Scott Pruitt announced a few weeks ago. And there, you can click on the links and you can get the paper that I mentioned that has the calculations and all those kinds of things. And there's also in there, it shows the cost of electricity from different sources. The most expensive way to make electricity is nuclear power. The second most is wood. More expensive than gas, coal, wind, or solar. The latter two are the cheapest two today. So there we are. Yes, ma'am.
So can I take from your presentation on the UK plant that they can get credit towards the Paris Agreement as a result of that plant, and what are you going to do about that?
Well, I actually did go over and I met with the staff director in the Parliament of it's called the Department of Energy and Climate Change, and I had an hour and a half long meeting with their whole staff, and I explained I had my 12 reasons why it's not carbon neutral, and she listened politely, and then she turned to the technical guy there, the modeler, and said, "Well, is what he said right?" He said, "Yeah, that's pretty much how it works." And then the lawyer spoke up, and she said, "Dr. Moomaw, you do not understand. If we cannot declare burning wood carbon neutral, we will be unable to meet our obligations to the European Union." Maybe with Brexit, they won't have to do that anymore. They have so much invested now. But I know that, I almost fell over backwards. I've been in this business a long time, but I thought that was, well, I appreciate it. I said, I appreciate your honesty. So
Just a quick follow-up, the agreement itself allows this?
It basically, it follows a set of rules which is a little convoluted. The rules are that if you burn bioenergy, which is, the ethanol in our gasoline, right? We're doing that too. But the Europeans are doing worse. They insist on biodiesel, and that's coming from palm oil in Indonesia, where they are deforesting huge tracts of land and burning vast forests to plant palm trees that produce palm oil, and they'll count all that as zero as well. And the reason you can do that is bioenergy is counted as a land use change, not as an energy emission. That means that Indonesia has to count it, or North Carolina, USA has to count it. Well, nobody counts it. You're supposed to acknowledge it, nobody acknowledges it. So it is quite a fraud, I think. And I worked with a group of scientists. We got 796 scientists to sign a letter to the Parliament of Europe saying, limit any bioenergy to the residues, period. Nothing more. The reason for that is that was the only amendment that was there that we could address. We would have preferred to say, just get rid of it, but we had to say that. We sent them another letter from a distinguished group of scientists in the US, a plea from American scientists. Don't do this, Till 2030, they're going to be doing it. So, I just think we have to keep making the point and working on it. I'm still working on scientist colleagues over in Europe who say, well, I think what they're saying is it's not our forest. It is really hard to convince them that this is not good. And so now that we have got several papers now with all the research, and the other side has nothing like that, I think we're going to be able to at least tilt the whole balance in the scientific community. Yes.
I always wondered, driving through the roads of northern England here, you get the patches of forest with small saplings.
Yes.
And other places that have tall trees.
Right.
What causes the difference? Is it the soil? And this is naturally natural forest, not planted forest. What causes the difference between trees that don't grow more than 30 or 35 feet and trees that get up to 7,500 feet?
It's mostly time. The question is, why do you, even if you go through a national forest or anything like that in New England, you'll find some forests where there are little skinny trees and other forests with big trees.
Yeah.
The difference is when it was last harvested. That's when was it last harvested? And so if the average age is 65 years, you're going to see a 65-year-old forest. If it was last 150 years, you're going to see a much bigger, taller forest. And if it was just done, 10 years ago, you're gonna see little tiny trees.
Well, it's in forest of tiny trees that never get any bigger.
Well, then that's probably soil limitation. Yeah. We have some pretty thin soils in parts of New England, over, you know, rock, ledge kind of stuff. Right. Yes. Yes.
What part of the carbon mass of a tree is the root system? And if you cut the tree, you know, and do whatever you're going to do with the tree,
Yep.
do you still at least sequester permanently the carbon that is in the root system?
You do for a long time, not indefinitely, but for a very long time. Here's something that really astounded me when I started really getting into this. So now the pitch of the forest industry is, well, we're going to use wood for more purposes, like building. We're going to use this cross-laminated timber, and we're going to build 14-story high-rises with it, and that will lock up the carbon indefinitely. Do you know what percentage of wood that is in buildings and everything else is still in that building after 100 years in the United States? It's less than 10%. Less than 10%. The turnover rate for houses in the United States is about 2% a year, meaning that we tear down after 50 years on average. The average lifetime of a house in the United States is 50 years. Now you say, well, Paul Revere's house is there in Boston, this has been around since 16, whatever. And that's true, but that's a very small number. And they're wood. Paul Revere's house is wood. So it could last. The point is it could last, but we're pretty wasteful. Let me just listen first. Yes.
Oh, I'm a member of the Lexington Tree Committee. After speaking to you, I have a lot of talking to do with my colleagues. But we do plant a certain number of trees in town. We're currently having an evaluation done of all the condition of all the street trees. So that will help us. But individuals in the town can request a free tree for their yard or as a street tree. We have quite a list now, and people can still do that. And they're working on using that list this year. However, the other thing that really depresses me right now is that in Lexington we are having a lot of tear-downs.
A lot?
A lot of
tear-downs. A lot of tear-downs of buildings, of homes.
Homes.
Yes, homes.
Yeah, to build large homes, pretty much.
Yes.
The tree committee does not really directly get involved in this, but there's a member at the town level that goes to meet with the builder to inspect what is going to be cut down. And there is a limit, and builders go over the limit and they pay the fines.
Yeah. Yeah.
And it is very depressing to see that happen. But it is very also rewarding to go out and meet with a local person who has requested a tree and put a stake in the ground, have DigSafe come, and the person sees the tree. And we really try to select trees that are more native and good to plant in our town. And we're just updating our tree manual, and it'll have a new list of trees. And people on the committee are going through this very, very carefully to enhance it. And it should be coming out this next year.
Oh, that's wonderful.
So that's a little bit.
Well, thank you for that.
You're welcome.
By the way, Lexington also has a wonderful wetland. It's right along the Minuteman Bikeway.
Right.
It's called the Arlington something, right?
Great Meadow. Great Meadow.
Well, but the point is, there's a great wetland there as well.
It's not ours.
Yes. And then, of course, Wilson Farm has some nice agricultural land here. It's not very big, but it's you know, it's good. You've got it all here. Yes.
The fact that big trees put on more weight than small trees,
Yeah.
it seems like that would have been known for a long time. Was that your engineering friend who demonstrated this?
He's the one who did the calculations that makes it so clear. Yes, this is not, look, this this isn't even something as simple as rocket science, right? I mean, it is so basic, and yet I hear it from foresters, I hear it from state officials, I hear it from people in the Forest Service all the time saying, we've got to, they look at any tree that's more than 50 years old and say it's over mature. I call them at an open meeting, and I said, wait a minute. Show me some over mature trees in this state. Now, I realize at my age I may have a bias on this, but show me. They were embarrassed. They were embarrassed. Yes.
So in view of that kind of thing, have you thought of publishing an article or a brochure that would be named something like 50 fallacies about forests and wood?
That's a good idea. That's a good idea. I hadn't thought of that one, but that's a good one. That's a good one. I'm sure we could come up with at least 50.
I'm sure you can come up with it.
Yes.
But as a means of getting that information.
Yeah. Well, I'll do it in my spare time. Yes.
Do you have any recommendations for the gardeners amongst us or people who have some property and how we can improve the property to be a better carbon sink?
Oh, very good question. The way you manage your lawn. I mean, your lawn may not be that big, but you add up all the lawns in a town, and it's a lot of land. I think in Herb Borman's book on the Great American Lawn, which he published back in the 70s, I think he said that the amount of lawn in the United States is the area of Pennsylvania. Right? Wow. And it has, and we put more chemicals on our lawns than farmers do. So there's a lot of work to be done here, a lot of education. But the way in which you manage your for example, making sure that the grass clippings go back onto the lawn and you don't haul them off and send them to wherever, and aerate the soil. Those kind of things do help increase the carbon content of soils. And then the trees that you plant on your property those are storing a certain amount of carbon. And if they're providing some shade in the summer, it means your air conditioning bills will be less. It means that actually the temperature, oh, this is interesting. You remember when Worcester had the longhorn beetle outbreak from China? On some wood pallets that came in or something, and they had to cut down, I think, 3,000 or 4,000 trees in the city. Somebody very cleverly got information on the electric bills of people in the neighborhoods that were cut down the year before and the year after. And I think it was 37% more electricity used the year after than the year before, when corrected for degree days. So this was not just it was a hotter summer, because they had to run the air conditioners more and everything else. So there's not many experiments like that you get to do, and it's nice to have one that really has the numbers and says, yeah, those trees are making a difference. They're doing their job. Yes.
So just speaking of cutting trees, as we're sitting here, there are people down the street here at Carey Memorial that are talking about the comprehensive plan for the town. Right. And I know some people in the Grove Street area realize that we don't have any kind of plan that includes forests, keeping our forested land. There was an issue where a person saved the land and the house and the forest as their retirement investment. So they sold that land to developers, I think 13 acres or something like that. And last week they cut 1,000 trees.
Oh, 1,000 trees.
Yes.
Yeah.
Now they promise they're going to plant some back, and but we need to pay attention to what's happening in Lexington in terms of this comprehensive plan. This was the first meeting tonight. They said that they're going to have future meetings. Be sure and sign the GWAC list, because we can keep you updated on when the future meetings are coming up. And if we all get together and we say, hey, this is important, they will listen. So just put that out there.
Plus that could have been meant to be 1,000 trees, let's say the average one, for 1,000 pounds. 1,000 is a million. That's a lot.
Let's take two more questions.
Okay, in the back.
So,
and then.
I was going to add to Fran's comment, because I live right near the Grove Street area. It's horrendous. They clear cut
giant trees. They're not as big as your largest tree that you showed, but huge old trees that were cut. And they're making, it's just clear cut all the way to the soil. Anyway, what I wanted to say is, what can we build into, or what is already being built into the Massachusetts Forestry Preservation Plan that we can then extend to Lexington and show Lexington, hey, we're part of this state. Let's not keep cutting down our trees, because there are other proposals that are out. I think I saw one on Waltham Street where they're planning to cut more trees and build more homes. I don't object to people, doing whatever they want to do with their property, but this tree cutting is really bad for everybody.
The question is about the amount of cutting of trees here in Lexington. The Amazon, the law in the Amazon is that you have to leave 50% of the trees that were on the property when you took it over, when you move into the Amazon. Those are Brazilians, by the way, they're not us. Those are those people who are destroying their forests, and yet they have a stronger set of commitments than we do. So I think we should be able to do it. I don't know specifically, this whole notion of it's called urban forestry, which may be a slight exaggeration, but having trees in towns and cities is getting a lot more attention. And in Boston and Cambridge, there's a program to bring trees to poorer neighborhoods. And what's absolutely fascinating is the enthusiasm of the people there of taking care of their tree. The kids, the parents, it's had this social benefit that nobody anticipated. And very few of those trees die. I mean, often in the suburbs, plant the street tree, nobody waters it, and it dies. They've lost very few trees in Roxbury and places like that in Boston. So I think, at every level, every income level, every community of whatever type, there's an opportunity to do something. And I think those of us who are fortunate to live in a community like Lexington really could be leading the way in terms of managing that. Yes?
Hi, I just wanted to put in a plug for mycorrhizal fungi. I don't know if you mentioned this yet, but that and soil crusts, two unsung heroes. And I've been reading some more and more astounding amounts of carbon locked up in the root system. There's, I don't know, I better not quote it, but just staggering. And I wonder if really this is where the folks should be. I know that the Department of Agriculture does have a great program, and they are getting the farmers to, low-till, but you have to somehow get the fungi in there, I guess.
Right.
So it seems to me that if anything, it's number one, this should be up there. And also preserving soil crusts, another astounding, I guess that's in drier areas. And so you want, more of a priority of not having dirt fights. So when you build a solar plant in the desert, you don't build giant roads. These are things that are totally unexpected to me, and they seem to be major, some of the leading, it says here right here, it dwarfs the microbial biomass in soil, a Springer paper here, that the, mycorrhizal fungi, the fungi are associated with every plant going back on hundreds of millions of years, and how plants got off the ground, how we destroy it. You destroy it when you overtill, you just really wipe it out with fertilizer. You basically have to leave things alone. But, that's really staggering to me how much, so that seems to me the number one priority worldwide has got to be promote agriculture with symbiotic, fungi helping the plants out as the way they used to before we came. Try to improve things too much.
I mean, remember, the bacteria and the fungi shall inherit the earth. I mean, there are all these staggering things. I learned that I have 10 times as many bacterial cells in my body as I do human cells. Oh my goodness. What's going on in there? Yes, Mark.
I was wondering if you could talk a little bit about our food choices and how we grow our food, what choices we make for our food, how they affect both the soil and the forest.
Well, a really good question. I mean, the assumption again is that we've got to have high-tech agriculture to feed people. And in fact, people are demonstrating that that's not necessarily so. How many of you have read Omnivore's Dilemma? Right, that wonderful talk about Polyface Farm. They're essentially doing the kind of grazing, this where he claims he's growing 4 times as many cows per acre as his neighbors are. And he calls himself a grass farmer. He manages the grass. And then the cows and the chickens take care of the process. And he just moves them around, gets them in the right place at the right time. So there are choices can be made. If you are a meat eater, a beef eater, well, the first step is grass-fed beef over corn-fed beef. Corn-fed beef is really bad. Just the amount of nitrogen fertilizer that is needed to grow the corn is what leads to the dead zone in the Gulf of Mexico, where there's this wonderful source of protein called seafood, and that's being wiped out to feed somebody, to feed cows so that we can eat the cows. But beyond just grass-fed, is it this sustainably grass-fed process, or is it just, they're out there overgrazing the pasture? There's no label for that yet, I don't think. Is there, Seth? I haven't seen it on anything.
Grass-fed, grass-finished.
No, but when it's done, say, savory style or something, it's the extra step that really gives you the sustainable production.
They're working on that.
I know they're working on it, but it'll take a while. But yes, our diet is very important in terms of influencing things, and the emissions from agriculture are enormous, and they are methane from cattle. That's a big source of methane. Ammonia from cattle, huge pollution problem in many parts of the country. So everything in moderation, I guess, is what I would say, and think about it. Henry David Thoreau said that he went to the woods to live deliberately, so that
But you had home for lunch.
He did, well, only for weekend. He said only for Sunday dinner. But anyway, so he went there to live deliberately, and that was in the 19th century. And in the 19th century, living deliberately meant living simply. In the 21st century, we do not live simply, but we could still live deliberately, meaning we think about the actions that we're taking and the implications of our actions. And I think in some ways, we would be more conscious of that than Henry David Thoreau was. I mean, after all, it's pretty easy to live in a little cabin and not make much of a mess. But when you're living as we live, most of us live, we make a lot of mess. And so we need to really think about that and live deliberately every day. Thank you all very much.
GWAC, and I just want to put a date in your mind, June 27th, right here in this room, we will have an Energy and Environment forum with all of the candidates running for Jay Kaufman's seat. So it's only going to be on clean energy and the environment, so I hope to see you all then. It's a Wednesday, June 27th. Wednesday.